All right, this is a video continuing to dive into the graphs of polynomials. So we talked about polynomial behaviors using their graphs to talk about those and key features earlier in Math 3. But now we're going to talk a little bit more about end behavior as well as kind of revisit turning points, which is those bounces that we talked about, as well as the degree of a polynomial, which comes from the possible roots of that polynomial. So the first pages of your packet really do give you kind of the guided notes that you need to make sure you understand a couple of key features here that we're going to talk about today. So in this, I'm going to kind of skip over the warm-up and get right into the lesson. Keep in mind that the degree of a polynomial is the highest exponent, the leading coefficient, which tells you a lot about as far as positive or negative behavior, as far as reflection of the polynomial's graph. And then we're going to use this chart real quick to kind of help us with some, I guess, some reminders on end behavior. Remember that end behavior is how the function behaves as it approaches negative infinity on the left and positive infinity on the right. So what is the graph trending toward? What are the y values trending toward as x goes to negative infinity or as x goes to positive infinity? So if you take a look at this first part of this first row of the chart that we gave you, the positive leading coefficient, that means the number out front of the highest variable, that number is positive, then my even degree functions are going to be some version of this where both arms are pointing up. And my odd degree functions are going to be some version of this where both arms are going in opposite directions. So that means regardless of which direction my graph I'm looking, the left side or the right side, the negative infinity side or the positive infinity side, for my even degrees, both arms will be pointing up. So the graph will be trending toward positive infinity. For my odd degrees, if that leading coefficient is positive, then as x goes to negative infinity, that's the left side, the y values are heading down to negative infinity. And on the right side, as x goes to positive infinity, the y values would be trending up toward positive infinity. But if that leading coefficient is negative, so that means that this number in front of everything, so in this case, if this number here, that where that 2 is, if that was a negative number, then we would have a reflection. So this thing would flip over the x-axis. So then this row right here with the negative coefficient is what would give us what's happening with our evens and our odds. So our even functions, if I have a negative leading coefficient, then both arms are pointing down. So regardless of which way you're looking, left side, negative infinity, right side, positive infinity, both sides of the graph, the y values are trending down to negative infinity. When it comes to our odd functions, then that our odd degree functions, I should say, then the arms are going to switch. So the left side, the arm will be pointing up. So as x is go to negative infinity, the y's are going up to positive infinity. And on the right side, that arm is pointing down. So as the x values go to positive infinity, the y values are heading down to negative infinity. All right. So when you take a look at these first couple of examples, what you should be able to pick up from here is what the end behavior should be. So as I try to sharpen your screen for you a little bit, sorry, that's a little bit not clear. What we need you to be able to do is just pick up what's important, which is the degree of the polynomial here, which will come from the highest power, and in this case it's 4, and then what the leading coefficient is, which is the number in front. All right, so the leading coefficient in this case is 1, and the degree of this polynomial is 4. So that means that I'm going to have an even function. So that means both arms will be heading in the same direction, and the leading coefficient is positive. So it's going to be some version of this top row, okay? So that means my end behavior will be as x goes to negative infinity, that's the left side, the y's are going up to positive infinity. As an x goes to positive infinity, that's the right side, the y's are also heading up to positive infinity, because remember, it's some version of this right here, this even degreed positive leading coefficient where both arms are heading in the same direction. Again, when we talk about end behavior, we're talking about where is the graph trending toward, way out to the left and way out to the right. All right, let's try this next example. I'm looking at the highest power, which is 5, and the leading coefficient, which is -3. Okay, so my leading coefficient is negative, so that means I'm going to have some version of this graph here where my left side arm is pointing up and my right side arm is pointing down. So that would mean as x goes to negative infinity, that's the left side, my y's are going up to positive infinity. As x goes to positive infinity, that's on my right side, the arm is pointing down, so the y's are trending down to negative infinity. So again, make sure you're taking note of where the arms are pointing when it's an odd degree function or an even degree function, as well as the leading coefficient being positive or negative. Okay, then we bring back this idea of bumps and turning points. Now keep in mind that the bumps is this idea, or we also call it bounce, the idea that I have a double root at that place. So my graph doesn't pass, my graph doesn't pass through that spot. It hits it and then it comes back down. It just touches it quickly and comes back down and changes direction. So it's a turning point, which makes us think, you know, it is a critical point. But when it bounces on the x-axis like that, that's an indication that it's a double root, possibly. So what we want to keep in mind is this idea about relative minimums and relative maximums is where the graph changes. And the bump here, the possible bumps, is this idea right here that I really want you to make sure you read through. The highest number of turning points. So that's where the graph changes. So that starts, stops, bounces, bumps, where it changes direction, goes up, comes down, comes back up. The highest number of turning points a graph can have is equal to the degree of the polynomial, so the highest power, minus 1. So that means if the degree of your polynomial is 8, then the highest number of turning points that it could have would be 7, because 8 minus 1 is 7. All right, so let's do a couple of examples here. So the degree of this first example is 4. So that means that 4 minus 1 is 3, which means the maximum number of turning points that this could have is 3. So if you look at these examples real quick, the highest power down here is 3. So then 3 minus 1 would give us 2 maximum possible turning points. Okay. Number 2, the highest, the degree of this polynomial is 6. Minus 1 is 5, which means 5 maximum possible turning points. Okay, again, the highest power is the degree. Minus 1 will give you the maximum number of possible turning points. All right. Then we bring back the idea of the degree of a polynomial looking at how many times it crosses the x-axis. So every time it crosses the x-axis, we call those things zeros or roots or solutions or x-intercepts. So all these x-intercepts, all these places that it crosses the x-axis, those are possible solutions or possible roots, which would give us the highest degree that it could get. Remember that a bounce would be a double root. So in this case, we don't have any of those bounces on the x-axis per se, but I'll do one of those examples with you real quick. But if I count here, 1, 2, 3, 4, 5, I had 5 times where I crossed the x-axis. So the highest degree here would be a 5 or a 5th degree polynomial. All right, again, fifth degree because it had 5 times that it crosses the x-axis. All right, let me sketch one real quick just to see if I can be helpful about this bounce idea. So if I had something like this, if I had some even function that looked a little bit like this, I'm focused on where it touches the x-axis. All right, now on just first glance, you might think that that's 3 times that it crosses the x-axis. But the reality is I have this bounce right here, and a bounce is double. So that means 2. So this would be 2, 3, and then 4. So a 4th degree polynomial is possible. So that's the highest possible degree that this thing could have. So I'm counting the places that it crosses the x-axis, keeping in mind that my bounces are double.